Okay, so we're continuing now with supervised machine learning methodology. Again, I'm Chris Vargo, and I'm excited to show you how machine learning applies to marketing text analytics. So the last lecture, we left off talking about training. We used my music mixing analogy, but how do we know when to start and stop the training process? All machine learning algorithms reach a point where they're perfectly tuned, or tuned to the best of their ability. This is the time where we want to stop training. This is where the loss or error in the model is minimized, and the model is producing predictions that most closely match the training and test data that it has been given. The challenge with training is that if you don't watch, most supervised models will eventually reach a point where they overfit. That is, they'll reach a point where they actually start to degrade. Validation loss is certainly the most accepted evaluation metric in the training process of machine learning and deep learning. But of course, there are many others. Loss is generally a synonym for what we call error in the social sciences. Simply put, it's the difference between the probability that our algorithm returns for a given document and the actual label. The higher our loss, the larger the difference between the model and the data set, and generally, the worse our predictions are. Supervised machine learning algorithms return probabilities for classification problems. So, the higher the probability, the more sure that the algorithm is that the positive class is present. The default binary cutoff for most models, and including all models in TensorFlow, is 0.5. So any document with a probability score of 0.5 or greater is considered to be a positive label for the positive class. So we'll go more into why algorithms return probabilities later. But to summarize, the loss is the mean probability error. It is a measure of uncertainty. The lower, the less uncertain the model was in general. In TensorFlow, you can actually see the training process as it happens. This model begins to overreact to the training data here at epoch 6. Machine learning models these days have so many features that a model can be perfectly fit to the test set, almost to the point where there is no loss. But that doesn't mean the model is good. In fact, if we fit a training set perfectly to where the total loss is 0, we will almost certainly have lost sight of reality. That's why we always validate our models against a validation or holdout set. It's also called a test set in the social sciences. After a model finishes a training step or epoch in deep learning, we need to check how our model performs on data that it's never seen. If it's truly improving, its stats on the test or holdout data will improve as well. However, it's been documented that to a certain point, the model will begin to diverge and begin to perform better on the training set than it did on the holdout set. This is the point where we've gone too far. To keep our music mixing analogy alive, this is the point where we've become tone deaf. It's time to stop training because we've reached the point where we are as good as we can be. Above is a standard output that we get when we're performing deep learning algorithms via TensorFlow. The cool part about TensorFlow models is that you can see the fit process happen in real time. The training epoch highlighted in light green here is our best epoch. Why? Because it has the lowest validation loss. In the following epoch, the training loss improves, but the test or validation or holdout, whatever you want to call it, data set gets worse. We've started to diverge away from reality. We're starting to become tone deaf. We're overfitting our data. Luckily, in deep learning, we're able to detect this point programmatically and stop training when we see this happen and restore the weights for the best epoch, here, epoch 6. This is called early stopping. And when in doubt, always use early stopping to prevent your model from being overfit. So there's two more metrics that I want to talk about here that really do apply to text classification. They describe the trade-offs that machine learning models tend to have when it comes to classification. We call them precision and recall, and they come from the information science field. Precision refers to our positive classification accuracy. Put another way, when you label something as 1, how often is it actually a 1? Take this example of news articles. The goal of this machine learning algorithm is to find fact-checking URLs inside of a collection of larger news articles. So, how precise is this model? The algorithm labeled one article as a fact check, and it is. So the precision here is 1 for 1. If it found one fact check, and indeed there was one fact checked, its precision is perfect. If it found 2, but only 1 was actually a fact check, the precision would be 50%. But recall pertains to the total amount of positive examples that the algorithm is able to find. Take a look at the second article here. It's a fact check, but our algorithm missed it. So there were 2 possible fact checks and only 1 was identified. Therefore, our recall is 50%. In an ideal world, we'd like to optimize precision and recall, but in reality, we can't. It's very important to understand for all classification problems what precision and recall means for your models. Imagine you're Apple. Your job is to build an algorithm that detects irregular heartbeats within your Apple Watch ECG sensor. You have a trained model that interprets a person's ECG and delivers a classification to them. Your heartbeat is regular or your heartbeat is irregular. What's important to understand is that in machine learning, we choose what to optimize for. We can't optimize for both. What should Apple choose to optimize for? Precision or recall? Let's consider the real-world scenarios. If we optimize the detection algorithm for precision, we'd only notify a person when we were very, very sure that their heartbeat was irregular. If we choose to do this, we're going to be conservative about what we say is irregular. Do you think this is a good idea for heart detection? Probably not. We want to detect every irregular heartbeat, right? Even if we're not totally sure. If Apple misses an upcoming heart attack, that is far worse of an error to accept than simply having a false alarm. A consumer might be really frustrated with a false positive, a heartbeat that's regular that we say is not, but at least they won't die. That's really why we want to make sure that we accept recall here. So recall is saying that we want to catch everything that's irregular, even if we're not totally sure if it's irregular. That's what maximizing for recall is, detecting all possible occurrences of the thing that we're interested for, maximizing for the number of positive classifications that our model returns for the user. Every problem that we tackle with supervised machine learning has different trade-offs. So let's consider another algorithm on the Apple Watch. It's News app. Apple can choose to send users push notifications when they think a news story will be relevant to them. So, do we want to optimize for recall or do we want to optimize for precision? If we optimize for recall, we'll send consumers a push notification for every single article that we think could be relevant to them. How do you think consumers would react to this? Do you like getting a ton of push notifications? Of course you don't. This is a classic example of us wanting to maximize for precision. Every single article we recommend should be extremely relevant to the consumer getting the notification, even if we have to sacrifice recall to do so. We don't need to show consumers every news article that they might be interested in, but instead we only want to show them a select few that we're sure they're interested in. So here, precision is the right answer. Machine learning models have parameters that are specified at launch. In a deep learning world, the 2 most commonly specified parameters are the learning rate and the batch size. Learning rate is essentially the degree to which we alter coefficients as we train. A higher learning rate means turning knobs more aggressively. A lower learning rate means turning knobs more delicately, a little at a time. Batch rate simply refers to the number of documents that an algorithm considers at once when trying to tune these weights. Both can ultimately affect model performance, so we'd be remiss not to try and tune them both. That is, find values that optimize the model's performance. Here's a visualization of how these tuning processes can really result in different performance metrics. Here, accuracy. These settings really do matter, and we need to try to do them. And finally, the last step of the machine learning workflow is to go out and predict new data. Once our model is ready, it's time to go use it. Let's walk through some examples of how I've used machine learning and considerations that I have made along the way. We'll cover this in our next lecture.